Hello, welcome to Basics of Finite Element Analysis Part 2. This is the fourth week of this particular course, and in the last week we had discussed the method of numerical integration, and we closed last week by discussing Gaussian quadrature integration method or Gaussian quadrature method. So, what we will do today is that in the first part of this particular week, we will continue the discussion on Gaussian quadrature, and we will actually do some examples which will make things a little more hopefully clearer as to how this particular process is conducted. And once we are done with discussing Gaussian quadrature and numerical integration as a theme, then we will start discussing about 2D problems having one variable. So, that is what we intend to cover over this week, and I hope this week, like previous ones, is a very beneficial exercise and endeavor for all of you. So, as I said, we will continue discussing numerical integration for starters. And if you remember, we had said that for Gaussian quadrature, if I have to compute an integral I within the limits x a to x b, and I have to integrate a function f x dx, then the first thing is that I transform this integral into natural coordinate system. So, my limits become -1 to +1, then f is still the same function, but x gets replaced by a function of zeta, and then dx gets replaced by j times d zeta. So, this is what we had seen, and I can label this thing as f hat as a function of zeta. So, this becomes -1 to +1 f hat zeta d zeta. So, this is, so now that I have transformed this integral in zeta space, then like other integration schemes, I can express this integral in terms of the values of this the integrand at specific points times some weights, and if I add up all those weights, then I get the integral. So, this equals f hat zeta I times w I, or actually instead of I, now I will use a little bit different subscript. So, it is, excuse me, zeta t multiplied by a weight w t, and this index is moving from 1 to r. It is moving from 1 to r. Now, it is important to understand that here this r is the number of quadrature points. For instance, in trapezoidal rule, we had seen that the number of quadrature points is 2, the first point over the domain and the last point on the domain. If I go for Simpson's rule, the number of quadrature points are 3. So, in Gaussian quadrature, it depends, we can choose whatever value of r we want based on how much accurate we want the integral to be. Okay. So, r is number of quadrature points. So, I can prescribe the value of r as 1, 2, 3, 4, 5, 6, 7, 8, whatever. Okay. W t is the weight corresponding to tth quadrature point. It corresponds to tth quadrature point. And f hat zeta t equals value of function f hat zeta at tth quadrature point. And zeta t is equal to coordinate of tth quadrature point along zeta axis. Okay. So, these are the definitions. So, these are the definitions. Now, to recap, we will see what these values are. So, as I said, r could be anything, it could be 1, 2, 3, 4, whatever. So, what we will do is, we will reconstruct this table. So, r for a specific value of r, what are the values of zeta t, and then what are the values of w t. R has to be, it will start from 1. So, when r is 1, then there will be only one quadrature point and its value is going to be 0, and the weight will be 2. When r is 2, then zeta t could have either a value of plus 5773 or minus 0.5773, and weights for both these locations is unity 1. If r is 3, then I will have 3 quadrature points. The first quadrature point will be located at zeta equals 0. The second quadrature and third quadrature point will be located at zeta equals 0.774596, and the weight associated with 0 is 0.8888, and weight associated with the other 2 points is 0.55555, and I can also have r as 4, and the weights, the quadrature points are, there are 4 points. So, 2 points are plus minus 0.339981, and the other 2 quadrature points are plus minus 0.861136, and this is, and the weights associated with these first 2 points is 0.65214, and the weights associated with other 2 quadrature points is plus minus 0.347854. Okay. And similarly, I can have r as 5, 6, and so on and so forth. So, now what we will do is, we will actually calculate, do some calculations. So, suppose, so example, so suppose I am interested in finding the value of k I j right. So, it is a stiffness matrix associated with some differential equation, and let us say its definition is integral from x a to x b some function a x psi I e psi j e, and it is actually differential of this dx. So, what does psi I mean? D psi I for eth element over dx. So, this is what I am interested in finding. So, I am going to erase this. Another example could be that someone may be interested in finding mass matrix for a differential equation, and if the definition of the mass matrix is such that it is equal to x a to x b b x psi I e psi j dx. And the third example could be a force vector f I e equals c x psi I e dx. So, again the integral is x a to x b. Now, here our aim first is the first step is, if I have to evaluate these integrals, is what should be the minimum acceptable value of r. So, our aim is to find minimum value of r, that is how many quadrature points should we use to calculate these integrals. So, minimum value of r, okay. That is the goal. So, minimum value of r. So, that is first, and then second step will be using that r calculate integrals, using that r calculate those integrals. So, I have to compute k I j, m I j and f I. Okay. Now, psi I is what? It is an approximation function. For whatever, let us say the variable is u. So, it is an approximation function for u, and this prime denotes that it is its derivative, right. Similarly, here also you have psi I j. Similarly, you here also you have psi I, right. So, here you have psi I and psi j, here you have psi I and psi j, but here you have only psi. So, for each of these cases we have to figure out what is the appropriate value of r. So, the appropriate value of r will depend on how complicated this integrand is, how complicated this integrand is. Okay. So, to figure out how complicated this integrand is, we have to identify what is the order of polynomial the integral involves. So, before we do that, we also assume so all these are 1s. Okay. Suppose we just assume that ax, bx, cx everything is 1, just to make things simple, but once we know how to calculate r, we can plug in ax and we can again recalculate the value of r. So, if ax, bx, cx is 1 and suppose interpolation function so it could be linear, it could be quadratic, it could be cubic, and so on and so forth. So, if okay. So, if it is linear, then psi I e prime would be a constant. If the interpolation function is linear, and when I differentiate it, this will be constant, right? And so will psi j prime also. So, so psi I times psi j will be a constant. What about dx? Because when we are going to do this integration, we are going to do it in natural coordinate system. So, dx gets transformed as j times d zeta, and we had discussed in the last class that if the line element is a straight, if the element is a straight line, then the Jacobian or j is constant and it is h over 2, which is the length of the element. So, we had shown that. So, dx transforms into j times d zeta, and the order of that is still constant, right? Order is still 0. Psi I times psi j is the order of psi I prime and psi j prime is also 0. So, P is equal to 0 in this case, right, which is, how do you calculate P? By adding up the order of psi I prime, psi j prime and j times dx. So, each of these is 0. So, P is 0. So, R is equal to P plus 1 by 2. So, this is half, but you cannot have half. So, you go to the next one. So, this gives you 1. Now, let us look at quadratic situation. If the psi function is quadratic, then psi I prime will be linear. So, order will be 1, right. Order of psi I prime will be 1, order of psi j prime will be 1, order of j will be 0. So, P will be 1 plus 1 is 2, R is equal to 2 plus 1 by 2, and that equals 1.5, but you cannot use 1.5 quadrature points. So, you go to 2 quadrature points. So, what that means is that if you have to find this Kij and your interpolation functions are linear quadratic, then the minimum number of quadrature points which you need is 2. If it is cubic, then what happens? So, if psi is cubic, then psi I prime will be quadratic. So, that is 2. This is also 2 psi j prime, and j will be still constant. So, constant means its order is 0. So, P is equal to 2 plus 2, 4. R equals 4 plus 1 by 2, and that gives us 2.5. So, I do not use 2.5, I use 3, which is the next integer. So, this is, so if I have to integrate, to get Kij, then I can use R is equal to 1 for linear functions, R is equal to 2 if psi is quadratic, R is equal to 3 if psi is cubic, and so on and so forth. Now, let us look at M. So, of course, here we had assumed that Ax is 1 or a constant. Now, Ax was a linear function, then in the first case P will be 0 plus 1. So, then R will be 1 plus 1 divided by 2, it will still remain 1, right. So, accordingly we have to recalculate R, it may or may not change. Now, let us look at M. So, in case of M, B, the order of B is 0 because B is a constant. What is the order of psi I for a linear function? 1. What is the order of psi j for a linear function? 1. So, P is equal to 2, and R is equal to 2 plus 1 by 2, and that gives us 2. Gives us 2. Let us look at quadratic function for psi. in that case, if psi is quadratic, then psi I order is 2, psi j order is 2, and psi j order of psi j is 2. So, this becomes 4 and r equals 4 plus 1 by 2, this gives us 3. And similarly, if psi is cubic, then p is equal to how much? 6. Then r is equal to 6 plus 1 by 2, and that gives us 4. Okay, that gives us 4. Now let us look at f. Let us look at f. So, when psi I is linear, then p equals, so I am saying that c is, I said that c is constant. So, its order is 0, psi I order is 1, and there is nothing else, right. So, then here p is equal to 1 and r is equal to 1 plus 1 divided by 2, it gives us 1. Next one, if psi is quadratic, then p is equal to 2 and r is equal to 2 plus 1 divided by 2. So, it is 1.5, so I go to the next number, it gives me 2. And lastly, if p is equal to 3, then r equals what? 3 plus 1 divided by 2, this gives me still 2, still 2. Okay. So, the point of all this discussion, and this is something we had shown in last class also, is that for the same differential equation, if the differential equation gives us different terms involving k, m and f, then while doing numerical integration, we have to actually do some calculation and figure out how many quadrature points we need, and accordingly prescribe the number of those quadrature points. So, this is important. So, what it means is that if psi is cubic, for p I have to, for k I have to use 3 quadrature points, for m I have to use 4 quadrature points, and for f I have to use 2 quadrature points. Now, if we want to be consistent, we can go with 4 quadrature points for k, m and f in all the cases, because that will not lead to loss of accuracy. But if I use 3 quadrature points, I will get correct answers for k, I will get correct answers for f, but I will not get correct answer for m. So, this is very important to understand. So, this is what I wanted to discuss in today's lecture. We will continue this discussion tomorrow, and till then have a great day.